Hello, welcome to a video on a theorem, an important theorem. The theorem is called Baire category theorem. First, let us state the theorem. Every complete metric space considered as a subset of a subspace of considered as a subspace of itself. See, we know that every space can be treated as a subspace of the same space. So we here take that the metric space as a subspace of the same space. Say subspace of itself is of the second category. See, a metric space is of a second category. Let's recall that what is mean by a second category metric space. See, if it cannot be expressed as the countable union of nowhere dense sets. See, as the union of nowhere dense sets, a countable union of nowhere dense sets, then that space is called it's called of second category. It's of second category. We say that if it can be expressed as the countable union of nowhere dense sets, then we say that it's of the first category. So we have a categorization of metric spaces into two: first category and the second category. What actually determines this categorization? It's the countable union or the possibility. It's the possibility of expressing the metric space as the countable union of nowhere dense sets. Okay. See, nowhere dense sets, actually the meaning of nowhere dense set is a set. It's a subset of the metric space which contains points, and these points are spaced. They are not packed thickly. They are not thickly packed. They are distributed points. We can say that in an informal way. We can say that. See, that's a collection of distributed points. So there is no way to accommodate an open set in such a set. See, what kind of set? So in a nowhere dense set. See, that means every nowhere dense sets avoids the presence of open sets. So since open sets are not present there, open balls cannot be present there. See, we know that open balls, open sets can be expressed as the union of open balls. Open set can be expressed as the union of open balls. So in that sense, we can say that, see, when a nowhere dense set avoids open sets, it will avoid open balls also. So they are at open balls and nowhere dense sets. Actually, they lay at opposite poles. Actually, so they have entirely different characteristics. See, their nature, their characters are entirely different. So one cannot accommodate the other, and one cannot make friendship with the other. That's the important property of these two, or the important distinction between a nowhere dense set and open sets or open balls. Okay. By discussing this, see, or thinking about this, or recalling this property of nowhere dense sets and open balls, let's begin this the proof of the statement, proof of the Baire category theorem. Once again let's go through the statement. Every complete metric space which is considered as a subspace of itself, is of a second category. See, an important matter here we have to note is that here we require the property of the metric space, an additional property of the metric space, that is, it must be complete. See, therefore it is very it can be said that this property it plays a crucial role in somewhere in the proof of the theorem. Okay. yeah, without this, that means without the completeness of without the property of completeness of the metric space, we cannot write the proof of the result. So you can see that it will be used somewhere there at an important place in the proof of the theorem. Okay. So let's now, and also we use a lemma, the previous lemma that we have discussed in the in one of the previous video. In one of the previous videos, we have discussed in a lemma. Let's go through that lemma also. Let's recall that lemma. That lemma states that a subset A of a metric space X, a subset A of a metric space X is nowhere dense. It's nowhere dense in X if and only if each non-empty open set, if and only if each non-empty open set in X, see, you consider any non-empty set, an arbitrary non-empty set of X, you consider that open set can contain, it contains an open ball. You know that every open set must contain open balls. An open set contains open balls. See, it's a union of open balls. We can express open sets as the union of open balls. So it is not an important matter actually. It's an ordinary matter. It's not a very important thing, special thing actually. We know that every open set contains open balls, or it can be written as the union of open balls. So let's now continue. Then if it contains an open ball, then if we choose an open, whenever we choose an open ball, then very easily we can choose whenever we choose an open set, we can very easily choose open balls. So there exists an open ball whose closure, whose closure for taking closure, actually we are choosing from the open set. When from the open set we can choose an open ball. If it is not possible to choose its closure, you can choose a smaller open ball. So by choosing an open ball, then you consider its closure. Closure means its boundary also. Then we consider the boundary of the open ball together with the inner part of the open ball. So that closure, and then its closure has the property that the closure will avoid that the set, that nowhere dense set. So if the set A is a nowhere dense set, so it will avoid. That means it is distinct from, it's different from A. The closure of that open ball, which exists inside the open set, which exists in the open set, then its closure avoids, or it is disjoined from A. That means intersection of the closure of that open set, intersection of closure of the open set or open ball, closure of the open ball and the set A is a null set. Okay, that is the lemma. We use this lemma. This lemma is very important. We will use this lemma in the proof of it's very important. Many places we use. Again and again we will use this lemma in the proof of the theorem. Okay, that Baire category theorem. Let's go through let's start the proof of the theorem. See, this proof will be developed using the method of contradiction. See, so in the at the beginning itself, we say that we are going to develop a contradiction. So in order to get if you want to develop a proof by contradiction, you have just to imagine that, you have to just assume that what the statement, or what the statement actually that we are going to prove, we must negate it, or we must assume that the negation of the statement that we are actually want to prove is true. So that will be done here also. So for that we suppose that. So actually what do we want to show? That we want to show that the complete metric space every complete metric space is of second category. See, every complete metric space is of second category. That actually we want to show. But we know that metric spaces are of two category, first category and the second category. So if the metric space is not of the second category, then it must be in the first category. So if we assume that the result is not true, if the Baire category theorem is not true, then the complete metric space, we have a complete metric space, that complete metric space must be in the first category, right? Okay, it must be in the first category. So we take a complete metric space, we choose a complete metric space, and for the time being we assume that that complete metric space is in the first category. It is not in the second category. We assume that we just assume that it is in the first category. That means we suppose that the theorem is false. So if the theorem is false, then see, let X be a complete metric space which is not of the second category. That means which is of the first category. Then when the metric space, the completeness property, we will use that after a few steps. See, now we will consider this the space, the set X as the metric space. Okay, it's complete also, right? Okay, the metric space X. The metric space X, it's of the second it's of the first category. Now we think that it is of the first, it's of the first category. What does it mean? If it is of the first category, then you should recall that a metric space which is of the first category can be written as the union of nowhere dense sets, of a countable collection of nowhere dense sets. It can be written as the union of a countable collection of nowhere dense sets. See, it is not finite, need not be finite, it can be infinite. So, but it can be counted. That's why we index it. Okay. We choose it as, or we write it as an index set. So therefore, since X is okay, now X is of the first category, the metric space is of the first category. Therefore, there exists a countable collection of nowhere dense sets. See, there exists a countable collection of nowhere dense sets whose union equal to the space X itself, the metric space itself. That is X equal to union of the countable collection of the countable collection of nowhere dense set is here. It is chosen as A1, A2, A3, etc. And that collection is, that family is written here n. N varies from 1 to infinity. What does it mean? It means that it contains member is A1. First member is A1 when n equal to 1. The second member is A2. Then third member is A3. Fourth member is A4, etc. And these are the each member is a nowhere dense set. Each member is a nowhere dense set, and their union. Moreover, their union of all these nowhere dense sets can give us the metric space X. So here you have a correction here. It is not small x. See here, this small x must be corrected as capital X here. It's capital X. It stands for the metric space. So you can write that X is equal to union of A1. Union runs over n. Union over n of an, or it's equal to A1 union, A2 union, A3 union, etc. So by choosing members of this collection. Okay. Now we are going to apply the lemma. Okay. We want to apply the lemma. I have told you that we will continuously throughout the steps of the proof, we will use that lemma at many places. See, the first application of the lemma, we are going to apply the lemma here. The space X, we take the space X, the metric space X. You know that the whole space, where the whole space is an open set. See, the entire space, since we consider the metric space, the whole space X that space is an open set. So treating that as an open set, X is an open set, and then X is an open set, and you know, the first member of the family, and we take the first member of the family. What is that? What is that element? That is A1. So who is that? That's A1. A1 is the first member of this family, and you take A1. So we take A1, and also we treat X as the open set, and then we apply the lemma. See, lemma says that you take an open set of the metric space. X itself is an open set of the metric space. Okay, then we can find an open. Then there exists an open. An open ball there exists. Since X stands X acts as the open set, so first we need to take an open set. Then only we tell about the existence of an open ball inside. An open ball which is contained in that open set. Okay, so then the first open set is X, and then there exists, by applying lemma, there exists an open ball B1, and that open ball is named B1, such that when we take its closure, and that is B1 closure, its closure is B1 closure, then B1 closure will avoid the first member. That's an over-dense set. Since A1 is an over-dense set, so it avoids. That means A1 intersection, you can write a step here. That's A1 intersection. See, A1 intersection B1 closure, or closure of B1 equal to empty set. So you can many steps are missing here. That's a problem with this proof, but actually this is enough. So these steps are enough to write this, to complete the proof. But for better understanding, you know, you can write more steps. So for that you can write that A1 intersection. See here, when you are doing your rough work, you can write A1 intersection closure of B1 equal to the null set. Okay. After that, you know, you can now think about, you are now going to the second step. So this is the first step in which we apply the lemma. So in the second step, we are going to the second step. In the second step, we are going to apply the lemma, the same lemma again. So we need an open set. See, to apply the open lemma, we need an open set and also an over-dense set. See, an over-dense set. So in the second step, we are going to choose the over-dense set. At the place of over-dense set, we are going to choose the second member of this family, that is A2. We are going to choose A2, not A1. See, because A1 was already considered in the first step. So in the second step, we will choose A2 as the over-dense set, and we know that all members of this family of subsets are over-dense. Okay, therefore the second over-dense set is chosen A2, and at the place of the open set, you know, you can choose you choose B1. If we choose B1 at the place of open set in order to apply the lemma, because it's an open ball. In the first step, B1 is an open ball, but when we come to the second step, and that since we know that we know that every open set is an every open ball is an open set. See, since every open ball is an open set, so you can select B1. Initially it was treated as an open ball, but now in the second step we will treat it as an open set. So in that open set, considering okay, you can find in that open set an open ball, another open ball. So that will be a smaller one, smaller than that, smaller one, or smaller when compared to the open set B1, because it is completely contained in it. So we can now in the second step, let's complete that the second step. So then there exists, you applying the lemma, there exists, or it's possible to find an open ball contained in the open set B1, and such that, and we can call that open ball by a new name, and that's B2. So because it is it's obtained in the it's in the second step. It is generated, it is used in the second step, so we can give that step number actually. So B2 is the new open ball, which is a subset of B1. B2 is a subset of B1, and then you can moreover we are going to compare it with the nowhere dense set A2, which is chosen in the current step. So but when we compare it with the A2, we can say that by the application of lemma. So these are done using lemma also. By applying lemma, actually we are choosing. We can choose an open ball B2. The second open ball B2, which is inside B1, is selected by applying the lemma. Again applying the lemma, we get that open ball B2, and that B2 has the property that it's closure. B2 closure, you consider B2 closure, and then that completely avoids the second nowhere dense set A2, which is chosen here, which is chosen from this set, from this family. Okay, therefore you can write that. Now at the end of the second step, you can write that B2 closure. See, B2 closure, you can write this step as B2 closure intersection A2. What is it? It is also the null set, equal to the null set. So B2 closure intersection A2 is the null set. Okay. Now we have this. We can now once again you can trace that steps, the previous steps. Thus we have, in the first step we have obtained B1, the open ball B1, and in the second step we have obtained open ball B2. Then again in B2, then we are now applying once again the lemma. The third, we are going to the third step. We can develop the third step by applying again the lemma and considering considering the newly obtained open ball B2, the new open ball which is present in the second step is B2, right? Okay, and that open ball will be used in the third step. And you can consider the third member of the family, and that is that is A3. So A3 is it's also an nowhere dense set. A3 is a nowhere dense set, and we choose that A3 in the third step. By choosing A3 and by using the open ball B2, which was taken, which was obtained in the first step. Here in the third step, it is going to be used as an open set. See, so using it as an open set, the B2 will be used as an open set in the third step, and then using A2 as the nowhere dense set, we can find a third open ball, that is B3. We can find an open ball B3 in the third step. That open ball B3 is obtained, but where is it present? It is present inside the open set B2. See, inside the open set B2, or from the open set B2, we can choose an open ball B3, such that at the end of the third step you can write that B3 closure of B3 will avoid the set A3 completely. So you can write B3 closure of B3 intersection A3 equal to the null set. See, this can be continued any number of times. This can be continued, but one more thing, very important thing, we have to say that, see, at each step we are choosing, when we choose open balls, see, one more condition we apply. See, the open balls chosen in the first stage, in the first step, will be of radius 1. See, suppose we have chosen, by chance we have chosen an open ball, a bigger open ball whose radius is greater than 1. We know that it is very easy to choose an open ball inside it. inside that that first open ball selected, you can choose an open ball, another open ball of a radius less than 1. So it's very easy. So in the first step, you should take care that the selected open ball will be of radius less than 1. Its radius must be less than 1. And the second step, open ball can be selected inside B1, the B2 open ball B2 can be selected, but this open ball selected must be of radius less than half, less than 1 by 2. See, that is 1 is 1 in the first step. The radius of the open ball selected must be less than 1 by 2 in the third step. So in this way, you can say that in the third step, then naturally the radius of the open ball selected, that is B3 must have radius less than 1 by 3, less than 1 by 3. So this can be keep going on, and this procedure can be continued, and you can say that you can after n steps, or after n minus 1 steps, then in the nth step, when you are in the nth step, how can we say that how can we develop that, how can we write that steps in the nth step, in the nth stage, or the step of the nth stage can be written like we can by considering, by applying lemma, and by choosing the nth member of the family, that is an, by choosing an, that is the nth member of the family. Of course, it is a Novair dense set. So an is a Novair dense set, and we have in the previous step we have obtained the open ball. An open ball Bn minus 1 is the open ball which is obtained in the previous step. So Bn minus 1 is the open ball obtained, but it has radius less than 1 by n minus 1, right? See, its radius is less, because B2 has radius less than 1 by 2, B3 has radius less than 1 by 3. So this can be going likewise. Then we get that Bn minus 1. So when you have the open ball Bn minus 1, then its radius must be less than n minus 1. We can choose it like that. Okay, its radius is less than n minus 1. Thus, but now but we are in the nth step. In the nth step, by applying lemma, with the effect of lemma, we can find an open ball. Here we are going to get an open ball. We can choose an open ball. That open ball can be named Bn, right? Okay, it can be named. It can be given name Bn, and its radius must be less than what? Less than 1 by n. Having a radius less than 1 by n. Okay, and moreover, it satisfies that condition, that closure of Bn must avoid the Novair dense set, which is in the nth step. What is that Novair dense set? It is An. Yes. So you can write that closure of Bn. Here you can write closure of Bn intersection An is the null set, equal to null set. Okay. And thus here. Stopping here, you can see that we are going to get, in this way we are going to get open balls, a sequence of open balls. So by choosing a family of Novair dense sets and applying the lemma, we have obtained now a sequence of open balls. First open ball is B1, having radius less than 1. Second open ball is B2, having radius less than 1 by 2. The third open ball is B3, having a radius less than 1 by 3. And at the nth stage, we have the open ball. We get open ball Bn. Its radius is less than 1 by n. Now it is clear that it can be continued. Up to which stage? It can be continued infinitely many times. This procedure can be continued. Yeah, indefinitely we can continue this procedure. Thus we get moreover, you can see that these open balls are nested. See, B1, because B2 is completely contained in B1, right? right? Okay. B2 is completely contained in B1, and then B3 was actually chosen from B2. So B2 is completely contained in B3 is completely contained in B2, and B4, next open ball will be contained is contained in B3. Thus you are going to get a nested sequence or nested open balls. We can say that it's a sequence of nested open balls, and that sequence of open ball is Bn, where n changes from n varies from 1 to infinity. See, and you know that every open ball has a sender, right? Okay, every open ball has a sender. Now we can think about the sender of but you know, the choice of the open balls. So since we choose an open ball from somewhere from the previously selected open ball, so there is no guarantee that all the open ball has the same sender. So that can vary. The sender of the open balls can vary. Okay, but even though these open balls are nested, see, the senders of these open balls can vary, and let's assume that the sender of the open balls are respectively x1, x2, x3, etc. See, that is what does I mean? Yeah, what do I mean here? I mean that the first open ball B1 has its sender be x1. It's a point of x1 will be a point of x. Yeah, of the metric space. X1 is an element of the metric space, because all these are happening inside that metric space. So x1, which is a center of B1, is an element of capital X. Then x2, we think that, or we assume that, let's take the center of the second ball as x2. X2 is the center of the second ball B2, and that's also in X. Then x3 is the center of, let's name the center of the third ball x3 as x3. x3 is the center of the third ball B3. That's also inside capital X. So this way we get the senders of we can choose the senders of the open balls, and we get a sequence. So because these are points, these are members of the metric space X, these are elements of the metric space X, and we can collect them, we can write them as a family: x1, x2, x3, the next element is x4, etc., nth element is xn, etc., up to, yeah, it goes up to infinity. Thus we get a sequence, and these senders are all present inside the respective, they are respectively present inside the balls, inside the open balls. And due to the condition we have applied on the radius, see, due to the condition we have applied, that we have chosen the condition that the open balls chosen at the nth stage has radius less than 1 by 2. So due to that condition we apply on the radius of the open balls, one thing is clear, that the sequence now we have obtained here, this sequence is a Cauchy sequence. That condition ensures that this sequence is a Cauchy sequence. Okay, so this is the point where we are going to apply the completeness of the metric space. Since we have obtained it as a Cauchy sequence, this sequence, what is this sequence? This is the sequence of senders of the open balls. See, and this sequence is a Cauchy sequence, and also since X, the metric space under consideration, is a complete metric space, you know that every complete metric space, in a complete metric space, every Cauchy sequence converges to some point in that metric space, some point in that metric space. So that's important. Since this sequence is a Cauchy sequence, and the space X, our space X is a complete metric space, and we can say that this sequence converges to one point. Say we can name that point as X. See, X, small x be that small x, this small x, which is an element of the metric space X, it converges to the sequence such that the sequence converges. There exists a point X in X such that the sequence Xn converges to that point. and since and also since x is the limit of that sequence, since x is the limit of that sequence, one thing is very very clear, that this point x must belong to each and every open ball. See, because xn, these values xn, or these elements xn belong to each xn belong to one open ball, and also all these xn's converge to the single point x. Therefore this point x must belong to each and every open ball. That is, x is an element of b1, x is an element of b2. What's b1? B1 is the open ball which is obtained in the first stage. Again, x in the limit point x, this limit x is an element of b2, x is an element of b3, x is an element of b4, etc. So x must belong to each and every open ball. Okay, therefore and thus we can say that since it belongs, and also we can say that x belongs to each its closure also, since it is the since x axis, the x is the limit of that sequence. Since x is the limit of that sequence, it's also clear that x must belong to the closure of Bn. For each value of n, for all n, it belongs to closure. See, because it acts as the limit of a sequence, so it must belong to it acts as a limit point. It has got the character of a limit point, so it must belong to the closure of Bn for each value of n. And therefore and also since x belongs to, now an important point we have to remember now, that since x belongs to the closure of Bn, due to this reason that x cannot belong to any of a1, since x belongs to Bn for all value of n, that is, x belongs to closure of b1, x belongs to closure of b2, x belongs to closure of b3, x belongs to closure of b3, etc. So for every value, for each and every value of n, x belongs to that closure. Therefore, since each of these closures avoids respectively the novaden sets a1, a2, a3, etc. We know that b1 closure avoids a1, and b2 closure avoids a2, b3 closure avoids a3, etc. This is true for all value of n. Therefore, since x belongs to each of these closures, so x cannot be a member of a1. So since b1 closure avoids a1, x cannot belong to a1. Since b2 closure avoids but b2 closure contains x, and b2 closure avoids or the intersection of b2 closure with a2 is empty set, so x cannot be a member of a2. So this is true for every n, for all values of n, and this is true, that is, x cannot be a member of a1, a2, a3, a4, etc. And in general an, it cannot be a member, x cannot be a member of an. That means x is an element of, x, x must be an element of x, since x is an element of x, but x is not a member of the union of, you consider the union of an. See, we consider the union of an, a1 union, a2 union, a3 union, etc. We also know that their union, a1 union of a1, union of a2 union a3, union a1 union a2 union a3, their union is equal to x. See, but this statement says that here we know that here we get that x belongs to x, x is an element of x, but since x is not present in any of an, x cannot be a member of union of an, union a1 union, a2 union, a3 union, etc. cannot contain the element x. These two statements are contradicting with each other. One way we get that x is an element of x, but the other way we get that x is not, because x is avoided by, x is present in Bn, in closure of Bn for all value of n. See, x is present in closure of Bn for all values of n, and but closure of Bn avoids an, and therefore x cannot be present in an, and therefore x cannot be present in union of an. But union of n is assumed to be equal to x. So it is assumed that union of n equal to x. Thus we get to non-agreeing statements. First statement is that x belongs to x, but the second statement says that x cannot be a member of x, which when written as x cannot be a member of x, which when written as the union of union a1 union a2 union a3 union etc. So thus we get the contradiction. So this is the contradiction that we were waiting for. So after obtaining this contradiction, we can say that somewhere we have made a mistake. So where we might have made that mistake, that might be the step where we have loosely accepted that the space x belongs to the first category. Or we have assumed that for the time being. I have told you that in the beginning for the time being we assume that it belongs to the first category. That is the real mistake we have made. So we have to correct it. So x must belong to the second category. Okay, that is the end of the proof of Baire category theorem. Okay, thank you.